Okay, question 2. We've got our ramp. We've got our thing, whatever it is, parcel, that weighs 4 kilograms. That's going to be pushed 2.5 meters up said ramp. The parcel weighs 4 kilograms. It's going with a speed of 5 meters per second. There's some resistance to motion, which is R, and we want to show that R is 2.8. So, and it does say in the question somewhere, use work energy principle. If you don't do work energy principle, you ain't getting any marks. So, firstly, we need a work energy equation, which is going to be that the kinetic energy lost as it goes up the rank and slows down is going to be equal to potential energy gained, so its practice going up, plus any work that is done. And if we can work out those three things, then we can work out the way we show that R is 8.8. So you need a 3-term energy equation. No more terms, no less terms, 3 terms. Now, some of these are relatively easy to piece together. We've got the kinetic energy, we can work that, we get that. That's a half mv squared, and we know the speed is 5. So a half times 4 times 5 squared is equal to the potential energy gained. Well, it goes up. It goes up that height. So if we know it goes up that height, we just have to work out how high that is. But that's the opposite. That's the hypotenuse. Opposite hypotenuse is sine. But so it's going to be the hypotenuse times sine theta. But we know in the question sine theta is 2/7. So the height is just 2/7 of 2.5. So the potential energy gained is mass times gravity times the height, 4 times g times 2.5 times 2/7. And the work done is force times distance. The distance it goes up the slope is 2.5 meters, and the forces overcoming is r. So that's 2.5 times r, and that gives us the whole equation that we then need to solve. All we then have to do is show possibly a couple of lines of working out that show that therefore gives you can imagine those lines of working out and write to yourself that r is equal to 8.8 newtons. I'd possibly want to write down a bit of working out there just to show that you know what you're doing, but actually you get the full A marks for having written down that line there correct and unsimplified, and probably I want to get as far as 2.5 r is equal to 22, somewhere in the middle, just to show that I'd done a sum and then got the right answer. And then part B, after coming to instantaneous rest, the parcel slides back down the ramp. So now the parcel's going up and then sliding back down the ramp again, up and down. So it's now going twice as far because it's going up and down. If it goes twice as far, then it's done twice the work. So we can then do a similar sort of equation. The kinetic energy after it gets back down again, i.e. here, is going to be equal to however much kinetic energy had initially, plus, not plus, take away the work done. So a half times 5 times v squared, the velocity is going on the way down, is going to be equal to a half times 5 times 5 squared, the energy it had when it started going up. take away the work done, which is the resistance force, which we now know is 8.8, times the distance, which we now know is 5. Let's just go up and down. And then we can rearrange that to get that 2v squared is equal to 6. And then we get the v is equal to 1.7 meters per second. So the kinetic energy there, when it's going down, is equal to the kinetic energy it had going up, take away whatever work was done. And then we can work out the speed going down. Part C suggests 2 improvements that can be made to the model. You need there's one mark for a valid improvement, and there's a second mark for a second valid improvement. We're modelling it with constant resistance. There could be variable resistance. For example, air resistance could be proportional to speed. We may choose not to model the parcel as the parcel as a particle, but instead we might be thinking about the fact that the parcel rotates as it moves up and down the slope. We might want to consider the dimensions of the parcel, anything like that. But the comments need to relate to the 2 modelling assumptions in the question. Air resistance and friction are already included in the non-gravitational forces. We're really looking at the modelling assumptions that are actually mentioned in the question.